we often want to generate constants in our code. So that's how we initialize variables, for example, and we just often use them. So one way to generate constants is by using the add immediate instruction. And so say, for example, we want to initialize this value a with the value minus 372. Well, we can use an add immediate. Here's the equivalent RISC-V assembly code, and we've chosen some registers for A and B. And so A equals, well, the 0 register, we know that holds 0, plus this 12-bit signed immediate. And so because it's signed, we can represent positive and negative numbers. And now let's suppose we want to do B equals A plus 6, B equals A plus this immediate value. But you may notice a limitation on this, right? So we know what the range is for a 12-bit signed constant, right? It's 2 to the 11 minus 1, and the negative value is 2 to the 11th minus 2 to the 11. And so, what if we want a bigger number that's outside of that range, or a more positive or more negative number? Well, we have 32-bit registers. We should be able to use that entire 32 bits, and we just need multiple instructions to do that. And so we can use two instructions, the load upper immediate instruction and the add immediate instruction. LUI, or the load upper immediate instruction, puts an immediate in the upper 20 bits of a destination register and zeros out the lower bits, lower 12 bits. And so here's the example. Suppose we want to initialize a variable, and int, this int keyword here says how we're going to interpret those bits. So these 32 bits, we're going to interpret it as, well, by default, it's signed. So int a equals means that's a signed number. And we could also say, well, we could have also said this is an unsigned int as well. So if we want it to be unsigned, we have to put that keyword unsigned. If we want it to be interpreted as unsigned. So here's our RISC-V assembly code. This single kind of line of high-level code, of C code, gets translated into two assembly instructions. And again, chose a register for holding A. We're going to load upper immediate. So this instruction puts in S0, puts FEDC8 in the upper 20 bits and zeroes out the lower bits. So after that instruction completes, that's what happens. And then after that instruction, we're going to add hex 765 to that. 765, this is sign extended. Well, 7 is 0, 1, 1, 1, so that most significant bit is 0. If we sign extend it, we're going to get 0, 0, 0, 0, a bunch of zeros in front of that. And so then we'll get FEDC8 0, 0, 0 plus this, and we finally get our entire constant that we want, our 32-bit constant in register S0. If we add those together, right? If we add those together, we get FEDC8 765. Okay, you may have noticed something here. Well, what if that 7 had been, a value that had, instead of 0, 1, 1, 1, that most significant hex digit here has a 0 in its most significant bit, meaning it's positive, so when we sign extend it, we get 0. But what if that had been a negative number? What if we had wanted it to be, something like F or something? 1, 1, 1, 1. Well, when it got sign extended, now we would have been adding all ones to, or F, 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 to that, F, 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 to the top part of that, the top 20 bits, and that's not really what we wanted. So we have to do the operation that if bit 11, that most significant bit of the 12-bit immediate that we're adding, is 1, we actually have to increment the upper 20 bits by 1 in the load upper immediate operation. So suppose we want this one, FEDC8EAB, And we notice, well, EAB is EAB, that most significant bit is 1. And so when it gets sign extended, we're going to get 1s all in the upper bits, up to 32 bits. And now we've got a bit of a problem. But if you remember, all 1s is like a -1. And so essentially, we're going to subtract 1 from that upper 20 bits. So if we increment that lowest digit by 1, so we're going to increment that top 20 bits by 1, instead of FEDC8, we put in FEDC9. Now, when we do this, minus 341, which is hex EAB, and it gets sign extended, right? And we add those together, that will get decremented. That top 20 bits will get decremented by 1. We'll get FEDC8 exactly like we wanted. So we can still do it in our 2 instructions, but we have to think about it. And if you look at code and you have your high-level code, it does that. And you look at the assembly that it got compiled to, and you get this, you're like, no, oh, that should be 8. How did that compiler mess up? Well, it didn't, right? It's because that second instruction, the add immediate, is sign extending that negative value.